time to join. Our our PE, thank you so much. We appreciate you. Then our speaker, we say thank you for finding time to do this for us. We appreciate you. Thank you so much. Then our chairman for today, Dr. Shasutogile, thank you so much for finding time to do this. For me, I call him His Royal Majesty, he knows why. So thank you for doing this for Warri chapter. And everyone has found time to join this call, and more will be joining. We say we appreciate you. Today's topic is interesting. We are going to be talking about beyond the black box, leveraging physics, informed machine learning for enhanced reservoir simulation and history matching. And I think we are going to learn something different from the normal today. And Dr. Shoes will be able to take us through that. And I say that sit down, relax, take your pen, take your paper, and see what you can jot while going through the topics. And we do this every month. NAPI do this every month for our different chapters. We do this for Warri chapter, for the Lagos main chapter, which is the headquarter. We do this for North American chapter, for UK, Europe chapter, for Uyo chapter, for Port Harcourt chapter, Benin chapter, Abuja chapter. So whichever, and we do the publicity secretary of NAPE do this as a bulk SMS and a bulk email to everyone. And please, when you see this email, endeavor to join any of the technical meetings, and you will see that your learning, your updates towards the oil and gas industry will be top notch. So we encourage you to always do this with us every month. And even as we go ahead, the announcement will show our conference and all that. So we say thank you for finding time to do this. And as we go ahead, you'll be able to learn more than you even expect to do. So thank you. Thank you so much. Then I call on the president. Can you see my screen? Okay. So I'll call on the president to go ahead with her speech. I believe she's on the.
Read the visit of the US. I want to print.
Hello, Dr. Obe. Dr. Obe, you can mute, please. P, are you there? P, are you there?
Yes, I'm here.
President, if you are there, go ahead, but that's not President's voice. So. Hello, President. So let me check if she's on the call.
Mr. Emmanuel Egbeli F. Nape will represent the president.
Okay. I didn't recognize your voice. Sorry, VP, you can go ahead.
Yes, good afternoon. Can you hear me?
Yeah, I can hear you.
I hear you, sir. You're welcome.
Thank you very much, Professor Juliet. Thank you very much to all the members of our Warri chapter. I think it's important for us to appreciate the effort that we take to organizing, these are technical meetings. And I think this should be the second or the first from Warri this year, which of course is very, very good. And they have seen the topic that is to be presented today. So I'll just make a brief remarks on behalf of the president, who of course is unavoidably absent in today's meeting. So this is to wish to carry on the best wishes of the president, to wish us well, to congratulate us on this continuing to keep the legacy of NAPE, which is, of course, having our ideas find oil and gas. And this, of course, we do through having engagements like this, technical engagements, business engagements. That way, we're also able to carry out all our objectives through be it the industry as well as the academia. Looking at the topic that we have here today, I have no doubt in my mind that it's definitely going to be an interesting one. And I believe that at the end of this, all the engagements that we are going to have would provide much, much more value to us, both in our individual endeavors, our careers, as well as even for the body of knowledge that we are going to have in the industry. So I wouldn't have to say much at this time. I don't know if there's any other task that will be assigned to me now, but I'm eagerly waiting to also participate and listen through, and hopefully also engage the speaker during the course of this presentation. So once again, I welcome everyone, and hope that we would also be able to enjoy the presentation. And more especially, as an association, we want all of us who are members to be members in good standing, to always be available for our activities, even as we look forward to our annual conference this year. Let us be active members. And for those who are yet to join us on this call, this is also an invitation to also join and become active and full members of this noble association. So once again, thank you, and I hand over the lectern back to the moderator. Thank you.
Okay, so thank you so much, Vice President, representing the President. Thank you so much. We appreciate you. So we'll go straight to the profile of the chairperson for today. We have Dr. Charles Otogile, is FNAPE, is a senior account manager LCB. Just a minute, my Zoom is blocking my screen.
Okay, you are introducing the chairman of the
yes,
event,
yes.
right?
Yes,
okay,
yes,
okay,
exactly.
can go ahead.
Okay, so Dr. Charles Otogile, FNAPE, senior account manager LCB. Dr. Charles Otogile is a fellow of NAPE and brings over 28 years of distinguished experience in the oil and gas industry. Throughout his career, he has consistently demonstrated excellence in subsurface data integration, providing critical technical support and championing workflows that enhance best practices in upstream investment decision-making. His expertise spans inland, onshore, offshore, and deep water basins, where he has delivered valuable insight into prospect ranking, well planning, and appraisal studies. Beyond his technical accomplishments, Dr. Charles is highly regarded as a mentor and coach. He has made significant contributions to developing the next generation of geoscientists within LCB and across the broader petroleum industry, offering guidance on exploration workflows, seismic interpretation, regional well correlation, stratigraphy, and sequence analysis. His impactful contributions as a geoscientist, thought leader, and career mentor are further evidenced by his published works in NAPE and AAPG bulletins, as well as his insightful presentations at numerous industry conferences. His comprehensive workflow documentation continues to influence petroleum exploration practices across Nigeria and internationally. He is currently a senior account manager with LCB. Please join me to welcome Dr. Charles Otogile as the chairman of today's technical meeting. Dr. Charles, over to you.
Thank you very much. Yes, can you all hear me, please? I believe I can be heard.
Yes, yes.
Thank you so much. Thank you. All right. Thank you, Professor Juliet, chairperson for Warri chapter, standing on the existing protocols. I mean, it's my pleasure to actually welcome everyone to today's technical meeting, where we will be exploring a very exciting topic, which is beyond the black box, integrating PDEs into deep learning architecture. And I mean, it will be good to see the new things that Engineer Chukwuebuka, Kizito, Duru is bringing to the table. I remember many years ago when I also did my research around this using neural network on how you train them. As you know, of course, the complexities of our reservoirs, especially in places like Niger Delta, where the easy oil have long been found. So today's presentation is introducing a new perspective, in my opinion, on how we can apply knowledge around AI and machine learning to improve our workflow processes. I strongly believe that this workflow would offer step change on how we handle data, accelerate history matching, generate some physical consistency in our reservoir insights, And all this we'll try to do in real time. I believe we're really fortunate to have such a presenter and such a great topic. So I encourage everyone to engage deeply as the ideas we'll discuss today would likely influence what we'll be doing now and in the future. So please, ladies and gentlemen, join me as we look through this topic, important as it is, and I believe it would help and deepen our knowledge. Thank you. Over to you, Prof.
No. You go ahead and read his profile, then
Okay.
you will present.
So for the instructor, the presenter for today, Engineer Chukwuebuka Kizito, is a production programmer with Renaissance Africa Energy Company. Chukwuebuka Kizito Duru is a multidisciplinary engineer and production programmer specializing in real-time production monitoring and hydrocarbon allocation, holding dual M-Engine degrees with distinction in petroleum engineering and electrical electronics engineering. So he leverages tools like energy components, GAP, Prosper, MBAL, and Python-based machine learning to drive reservoir optimization. A published researcher and author of the Reservoir Fundamental series, Chukwuebuka has a proven track record of optimizing asset values, a recognized thought leader in Niger Delta energy sector. He serves as the industry collaboration co-lead for SPE Warri Section 104 and is a dedicated member / volunteer of NSC, SPE, and NAPE. He is committed to advancing digital workflows and fostering industry-wide collaboration to shape the future of energy recovery. Ladies and gentlemen, please join me to welcome Engineer Kizito Duru. Over to you, Engineer Kizito.
So much, Dr. Charles. It's really a privilege to have my profile being read by you. I don't know why they made you do that, but thank you so much for granting me that privilege.
No, it's my pleasure. It's my pleasure.
Thank you so much, sir. Okay. Good afternoon to
So
our president.
I'll stop sharing, so you can share for your ends.
Okay, ma.
You can share for your ends. Thank you.
Can you see my screen?
Not yet.
Okay, let's see.
I can see it, but you're not on the first page. No. Yes, okay.
Yeah, I think we can see the screen now.
Okay, that's perfect then. Good afternoon, leaders, to our president, Mrs. Olajumoke, to the VP, Mr. Emmanuel, thank you for being present, sir. To our mother in Warri section, Mommy Juliet, good afternoon, ma. Good afternoon, Prof. And good afternoon to friends, guests, and students on this call. My name is Chukwuebuka Kizito Duru, as my boss, Dr. Charles, have rightly said. And today I'm going to take us to beyond the black box. So, one of the important, the slogan of NAPE is our ideas find oil and gas. So for visitors and new members and my colleagues that joined this call, please, whenever we say NAPE, we say our ideas find oil and gas. So NAPE, please unmute. I want to hear
oil and gas.
Our ideas
oil
find...
and gas.
Okay.
Oil and gas.
Okay. So for today, we have all heard that data is the new oil. But in reservoir engineering, data without physics or data that does not respect the laws of physics is basically nonsense, right? So today, I'll be lecturing us on how to make our deep learning architectures interpretable and transparent. I'm sorry, I had a busy weekend, so I'm gradually losing my voice, and I hope I am clear and fluent enough for everyone to listen. But if I'm not clear enough, please draw my attention to it. I prefer my class being, what's it called? Discussional or conversational, so that we learn and I also get to learn something new. So the journey is very simple. I intend to make us move from the black box to the glass box. So like we all know glasses are transparent and you can see whatever is inside. So unlike opaque black boxes. So first, let's start with the subsurface trilemma. We have our traditional finite volume models like Eclipse, T-Navigator. We have our pure machine learning models, which in this case, I prefer to describe as black boxes because that is one of the biggest problems of machine learning models. Most students and researchers have a situation whereby they have a problem, they wrote a couple of codes or built a model, their problem or the data set passed through that model and they get their Y, that's their result. So they have an X that passed through a model and they get their Y, but they don't know what happens inside that model. They cannot completely interpret what happens inside that model. Unlike our traditional finite volume models, which are basically incredibly accurate. Please forgive my use of the word perfect because I know they are not exactly perfect, but they're incredibly accurate. And because they are built on physics, they are highly interpretable. So you can decide to use your pen and paper and do that calculation, and you will most likely end up with the same result, maybe plus or minus 2 variance with what your Eclipse, Mbala, or what's it called, Petre RE has calculated, right? And because they are built on, I think there was a time, it's very important to recognize that there was a time when most of the things we do with technology these days were done with hand-drawn or handwritten. It was either Dr. Baker or Dr. Akara Jones that was narrating to us how he used to dictate forts, printed subsurface maps. So, but now with Petra, you can do this. Yes, obviously, in days or in weeks, but it's faster than it used to be before. And yes, with machine learning, you could do it in seconds. But despite you could do it in seconds in machine learning, the consistency with physical laws of what's it called? Mass conservation, Darcy law, or even fluid flow in porous media. It's difficult to interpret, it's difficult to prove that your model obeyed those laws. And those laws are real, those laws are true, right? Now, that is where we come in with the physics-inclined model of physics-informed machine learning models. So yes, physics-informed machine learning models are also fast, low seconds, because they're not entirely throwing away the neural network, right? But their consistency is high. So if you take up the values or the results you get from your physics-inclined models and hand calculate, the variations will just be maybe plus or minus 0.2 as the case may be. The data requirement is very low to medium because unlike most machine learning models that we keep telling you requires large chunk of data, because the more the data, the better the model. Since these physics-informed models obey physical laws, if you have at least reasonable data, you get to have good results. And yes, they are interpretable because they obey the laws, right? But before I go deep into my lecture today, I would like us to note that there are various ways of teaching physics to AI. It's not just a one should fit all, right? So there are various ways. We have the observational bias method, which is basically data dependent, which machine learning models use. But the problem with that method is, if you ask every student on this call and every other researcher on this call, they will tell you that they don't have enough data, right? In short, some publishers would reject your research paper if you don't build your model in at least 10,000 data points. So if you don't have up to 10,000 data to train your model on, your research might not scale through. So, and then you ask yourself, how many students, for instance, have access to such large data chunks, right? So we have the observational bias, which is data dependent. We have the learning bias, which is loss function dependent. And we have the inductive bias and architecture. And for today's lecture, I will focus more on the learning bias and inductive bias. I will double through the both of them for the sake of time. And maybe I will pay more attention, not maybe, I will certainly pay more attention to the learning bias, but I will certainly touch a bit on inductive bias and give you an idea. So, but for a background, the basic difference between a learning bias method and inductive bias method is that the learning bias constraints allow the neural network to remain as it is. So you build a neural network, maybe a supervised model, a reinforcement model, as the case may be. It allows it to remain, it's a hybrid method. So it allows the learning, the model remain as it is, but it constrains it all around with physics. So if your model gives up a result that does not obey physics rule or goes beyond physical rules, there will be a backpropagation and there will be a correction, right? It instantly corrects it and prevents it, right? Why for the inductive bias? The inductive bias brings in the physics from the beginning, from the foundation. So the entire pipeline obeys physical law. So that is just the basic difference. So one obeys physical law after the model has been built and trained. One obeys physical law or recognizes physical law from the very beginning, right? So let's move forward. So yes, this gives you an idea of the learning bias. Let me see if I have my, yes, I have my, so this gives you an idea of the learning bias. So you have the neural network in the middle in the box, and it's constrained by physical laws. That's the law, mass conservation, diffusivity, and the rest. So the PDE is basically a regularizer. The partial differential equation, as the case may be, with respect to whatever problem you are trying to solve, serves as a regularizer. So controls it and ensures that it doesn't abandon physical law, it doesn't exceed physical laws. So it's basically a hybrid approach, like I rightly noted before. And this also tells you the same thing. So the result is simple. Every prediction exists within physically consistent solutions. Every prediction exists within those physically consistent solutions, merging rigorous determinism with stochastic deep learning. So your physics laws is being merged with deep learning in this case. But then, how does this really work? Unlike our normal machine learning models that look at only the loss functions with respect to data, observational terms. So you get to read a lot of machine learning papers and you get to see only MSE, that is mean square error, or RMSE, that is root mean square errors, and so on and so forth. A physics-inclined neural network or a physics-informed machine learning model also recognizes the PDE. So in this case, what the PDE does for us is, it is for all of us, both geologists and engineers, we all agree that a good chunk of our reservoir data are not observable. So a lot of data is still logs underground that you cannot see, you cannot, work with, or you don't even have them, you don't even have such data as available. But with PDE, respecting physical laws, you will be able to predict those data, right? So those points are called collocation points. Collocation points are points within your reservoir that are unobservable or you don't have data available for. So your PDE properly helps you to calculate what is likely to be obtainable at those points, respecting physical laws. And the loss function with respect to that calculation is recognized. So the loss function with respect to that calculation is recognized. Then it also recognizes the loss function with respect to the boundary conditions and the initial condition, right? So that you said that you have a reservoir, say in, in Warri, for instance, that obviously not every part of the Warri landmass has fluid, right? So there are boundary conditions. There is a boundary to that. There is an initial condition to that. And these are also respected in the loss function or when calculating the loss function by this model. And yes, this also says the same thing. We have the model, the machine learning model on its own, which brings out a result or which runs out a result that the PDE validator constrains and ensures it does not, exceed physical rules. And if it does, there will be a back propagation correction. So it immediately forces a back propagation correction and brings out a result that is more physics inclined or that will base physical laws, right? here in every machine learning architecture, right, we have our soft constraints. You build your machine learning and you as an engineer, you realize that there are certain constraints to that model or to that problem you are trying to solve. And in this case, we'll call them our soft constraints, and they are over here, right? But then we also want these models to not just respect the soft constraints that I have recognized and just give me a result. No. So we force it to obey physics laws, and these laws are hard constraints. They are the architecture. So they are mathematically baked into the neural network itself, and the physics cannot be violated regardless of the optimizer part. So this optimizer, even if it was coming from the soft constraint, is forced to end up at the mean point, the medium. So it goes and ends up at what's it called? At the mean point. Yes, that should be the word I use. So it ends up at the mean point, respecting the hard constraints and the soft constraints. Unlike our traditional method. I know my boss from SLB will be wondering if we are trying to replace Slumberg's softwares and the rest. We're not trying to do that, sir, please. So please tell Slumberg that we have no such intentions to replace their softwares because they are good. But unlike what we have today, where we have to guess our values, maybe we guess your permeability and porosity, if that is what you are working on, or if that is the value you don't have at the moment, and you run your NCAF, that is your history matching and the rest, and you simulate forward and you compare errors with the results, checking your history. And obviously, at first trial, you obviously might not get the desired result. You guess again and you continue. So you continue this cycle for thousands of computational heavy forward runs. So you just continue thousands of trial and error. You just keep trying and getting on until you get close. Yeah, obviously, using your knowledge of engineering and geology. But unlike this, spins treat reservoir properties as trainable parameters. So instead of just predicting one permeability, one porosity, just tell me, okay, Kizito's reservoir is just 25% porous. No. We realize that at various points in the grid, the porosity at various points are different. And as the porosity are different, so is the permeability at various points in the reservoir different. So this treats these parameters as trainable. So every heterogeneous parameter is treated as a trainable parameter. And it does not use an adjunct code. You don't have to build a machine learning, you don't have to, build a new code or a new pipeline to help you do that. No. It is a single model that does these two things. So it trains and corrects immediately, propagates and almost instantaneously, right? So it's a continuous permeability map. It gives you a continuous, instead of a single permeability as you have here, you end up with a continuous permeability map with different values, XYZ, right? But then let's bring this back to a Nigerian. I've given us the general overview of physics-informed machine learning models. But let's bring this back to a Niger Delta. In many Niger Delta brownfields, the number of unknown reservoir parameters far exceeds of the observational data points, as I've noted earlier. So what we know is less than what is actually available on the ground, right? But to achieve this, or to at least interpret what is available on the ground to the best of our ability, we have to use physics as a governing equation, as a structure, physics being a governing equation. So our various physical equations will act as a structural regularizers, constraining the neural network to a low-dimensional physical manifold. So this basically prevents the model from overfitting. It prevents it from just memorizing values, right? So you get to see instead of the normal situation whereby your model has seen numerous values and just memorize it and say, okay, if A, B, and C appears, that means the answer will be D. But what if A, B, and C and E appears? What happens? It might still give you D as an answer if that model was not trained on the constraints of E or stuff like that, or any other data point. But in this case, it will apply a physical law and ignore the noise and give you a result that obeys, that obeys physics, that obeys those physical laws that you are trying to make sure you follow, right? Because those laws are true and those laws are real. And to achieve this, we also, in the Niger Delta, we also have to consider the weight of our model, right? So like I initially noted, our finite volume models are heavy. They are quite heavy. If you don't have a good laptop or a good system, whether laptop, desktop, or so that have good memory and the rest and good RAM and good processors, you might not be able to run a full simulation of your asset or or a particular reservoir, right? So, but if the best way to solve this, or a method in which this is easily solved, is when you pre-train your model with physics. So if you already pre-train your model with physics and you have a, what's it called, a lightweight model, which I think the next slide explains. Okay, I think it's the next 3 slides. Okay, this explains it, so I'll just come back to this later. Let's go forward. I will skip this now and explain it in the future. So for here, to give us a picture of what I've been trying to describe since, with my bad voice, please forgive my bad voice today. I'm gradually losing my voice. So to give us a picture of what I've been trying to describe since, this is, let's see this as, or let's imagine this as our, what's it called, our subsurface with our fluid flow, right? And let's imagine this to be the result our machine learning model gives us in the attempt to replicate this. So yes, it gives an idea of where the fluids are flowing, right? You're able to interpret it. Then let's see this as what the physics-informed model will do. So the physics-informed model recognizes, it's not perfect, please. I like to emphasize that fact. It is not yet perfect. So there are various rooms to improvement. We are not done yet with machine learning. We are not done yet with AI. There are various rooms for improvement. So you could see here where my pointer is a little different from this, right? So we could say it's about 96% close to the reference or close accuracy, right? It gives you about 96% accuracy. But this is obviously better than this. That is very obvious. So by enforcing Darcy law or any other physical laws, the P mathematically infers the permeability in this case, right? Secondly, for this, I would like to explain it on the next slide. So take it, if you have this slide, please, I sent this slide, I think, last weekend. You can read this up, but let me explain this using this for you. So we have, for our finite volume models, our finite volume models interpret our reservoirs or our subsurface as grids, right? I guess that is public knowledge to everyone here. And since it relies on grid base, it takes a point in the grid, right? So it takes a point here, and maybe goes here and takes another point, and so on and so forth, through the curve, right? Through the known region, right? But this obviously has errors because it has a massive mesh error because you get to see a situation whereby the permeability here is obviously different from the permeability here, right? And so on and so forth, all through the various points. But then we have the automatic differentiation, which leverages exact chain rules, that's PDE, via what's it called? Internal computational graphs. So it covers a larger margin, right? And covers a larger margin here, so the more you apply it, the more margin. So I could easily, put one here and also get this margin, right? And know the entire permeability in this. So, like I said earlier, it gives you continuous permeability. It doesn't just give you at a point. No, it gives you at this point, at that entire region that you have mapped out, right? At least to the best of its ability, because I like to emphasize it is not perfect yet. It is better, yes, but not perfect. So, comparing physics-informed neural networks to our traditional history matching, we have a situation whereby we just guess our permeability, run heavy simulators, depending on the number of times we have to do this, compared to history, and the cycle continues. So you tweak, you guess again, you tweak, you compare, you repeat 1,000 times. You keep doing this for every time you want to predict your reservoir address. But in this case, we have a feed production data plus PD. So basically the properties like permeability and porosity are treated as trainable functions, right? These are treated as trainable functions of the subnetwork and not fixed grid inputs. They are not fixed. They are trainable functions. And it's also correct. So as the results are coming out, there's back propagation, right? So it solves for a continuous high resolution spatial function, capturing geological features smeared by coarse traditional grids. So it captures the features, captures the collocation points, as I've initially pointed. So like I defined earlier, collocation points are points that you don't have data for. But this captures those collocation points as best as it can and back propagates if what our neural network was giving us is outside physical laws. So you could see the red line going and the blue going back. And you could see this dash here shows you that it's doing this fast. It's doing this fast. So it saves us a lot of time, right? And we have, and obviously back propagates errors directly to permeability parameters instantly, entirely removing the needs for complex adjoint solvers, right? So instead of you manually tweaking, it does it itself, it propagates itself and gives you, and your output is a continuous permeability field, not just a single permeability point, but a continuous permeability field, right? So the point I wanted to make earlier was about the weight or the heaviness of the information we have or the data we have to, process or simulate, as the case may be. So you could easily do this in 2 steps, right? You could, if you have an asset, let's say you are trying to implement this in your company, assets on asset level, you already have maybe a little bit of history of that asset. You could train it or build this offline, train the physics model offline, and it will produce for you a lightweight surrogate model. Now, this lightweight surrogate model can be in your phones, your tabs, and so on and so forth. And with continuous production data you are getting from your field and the rest of new information you are getting from your laboratories, you could impute that and get updated information, get updated graphs, updated results of your system or of your assets, right? Now, one point I would like to make here is we always have the issue of engineers or geologists telling us that machine learning is trying to, or AI is going to replace them. Please, AI does not, we as builders of or practitioners of machine learning do not have an intention, at least for myself, I know I don't have an intention to replace any engineer. Instead, my intention is primarily to make your job easier, faster, and reduce the redundancy in your job and more efficient. That is primarily the job here for me. So we have, and for Dr. Charles, we are not trying to replace Slump-Veggie softwares. We are basically trying to complement them. So pins are not obsolete infinite volume models. No, they are acting as unprecedented accelerators to find the most likely candidates. So instead of guessing inputs or guessing the permeabilities or any other input you want to put in your simulators, you can easily test them in, on a pin model and compare the results with your numerical solvers, right? So you can do a high fidelity check. So after doing it here, you can always check it up here, a high fidelity check, and you get to see a larger picture, a better picture of your reservoir or whatever data you are trying to analyze, right? So for petroleum engineer, we are shifting your job from manual grid tweaking, sort of tweaking and tweaking every time or guessing data, to advanced objective function engineering. So you are focused more on your engineering job, thinking and solving a physical problem or constraints that you find in your design or in your system. So the strategic value for our energy climate is simple. For a marginal field, it enables rapid evaluation of newly awarded blocks. NUPRC newly awarded blocks in January. So it helps you to rapidly evaluate those blocks faster without requiring massive high-performance computing, clusters, or even extensive historic data. So for those newly awarded blocks, you don't even have historic data for the first place. But with these models, you can evaluate them and make engineering decisions from them, right? Why for brownfields, like we operate in Renaissance, it excels at identifying bypassed oil in compartmentalized stratigraphies by enforcing strict fluid flow rules across sparse or noisy well logs and noisy well logs. But at the same time, it saves us a lot of cost and compute efficiency. So you don't need to have large, every of your engineers in your workspace having heavy computers with heavy processors and so on and so forth. No, you just need maybe just one central heavy computer that does the initial training on that asset. And with the lightweight model, you can continuously simulate and get results because you have already paid attention to the boundary conditions and initial conditions of those of that asset. So yes, I have gradually taken you. Yes, I tried my best to make this as simple as possible because I understand we have a mix of audience. So I avoided going too deep technically. But I think I have taken us from our black box that is opaque that you can't see to our transparent glass box that we basically increase shareholders' trust. And this box is physics anchored, is data efficient, and for all engineers, efficiency is certainly our goal. Thank you so much. And the most successful models of the next decade won't just memorize data, so that it's not just about pumping in data, but they will understand the earth. They have to understand the earth because the future of reservoir engineering is physics-aware AI. Thank you so much. And here are my references on some other researchers that also talk to this point. Thank you.
No, thank you so much, Engineer Kizito. I really enjoyed every bit of it. Again, because this is one area that I am on a personal level very passionate about as well. So really good, and I mean, you presenting this took my mind back. I remember my MSc research was basically on neural network and how you train this and all of that. That was what I did my MSc research on years ago. So you bringing all of this and me seeing the improvements that have come up with new technology on the things I had done back then was really quite exciting. A few comments I will make before I get into summarizing the presentation, very brilliant presentation made by Chukwuebuka. And quick comments for me on one, about AI replacing jobs. Please, everyone, I will reiterate again, AI is not replacing anybody's job. The only people that AI will replace are those who refuse to learn AI. So if you know how to use AI, trust me, your job is still your job. Machines are still machines. So there's nothing about job risk for anybody. And again, I don't think what you've presented is to kick the likes of SLB and all the other servicing company who provide software out of the window. No. Softwares are always open. And if I speak for SLB where I work, this is not a campaign for SLB, please, so forgive me, but just wanted to respond to Chukwuebuka. Our softwares are open and they are scalable, and the idea is whatever new improvements you have, it can run on top of it. At the end of the day, it is making sure that the engineer or the geoscientist is able to find more for less. That is what the goal is for everyone. So having made those two comments, I'll just make a quick summary of this very excellent presentation. One is being able to show why you find a bit of failures in the traditional method of how we do things, having to do series of iterations and relying on so much data. So the message clearly is, with less, you can do more. You don't need to have one gazillion size data in order to show accuracy of what you do. He's also able to show how you can embed the PDs into AI, with special product, with very sparse data, with some good governance and some proper training, you can produce a better result, not minding the various boundary conditions that are set. From a mathematical perspective, in terms of looking at the mathematical architecture, again, it's shown that even though there are some data mismatch in terms of some wire locations, but with good residual constraint, you can be able to overcome those kind of things. Hard and soft enforcement of boundaries and initial conditions can also be applied. He also showed us again that the autonomous parameters can be identified, where P naturally performs gradient-based modeling, allowing the network to learn the porosity of the field, the permeability of the field, and also reservoir properties, and that they are also really trainable, again, with good example on the automated differentiations, as against the legacy one where you have to be picking special points, and then you might even miss out some areas where the PoroPAM could be better than the other. Another key point that was also brought out from the presentation was solving the sparsity challenge in terms of data, which could be noisy, which could not be enough, and also the pre-training of your numerical models, which when embedded, leads to 5-star convergence where there are limited field data. Okay, that was able to show, which I think is also very, very strong points. In essence, it's just saying that the pin operates on a low dimensional physical manifold, allowing for reliable prediction with minimal measurements. And we went for that to state that the accuracy is very good, even though, of course, like everything, AI and ML, there's still room for improvement. And that's why, personally, I took us back to something I did many years ago and getting to see the improvements that apply today. Another key point you raised was also the real-time intelligence that is applied to this. That once trained, pin-based digital twin can help to evaluate well tests. You can look at your choke optimization, your gas lift scenarios, and again, flooding if it's happening in your reservoir, and what the response for that would be. He also was able to show us how the hybrid workflow and the human element of it can be interwoven, right? With PIN, you can rapidly search for parameter spaces. You can have some very high fidelity simulators to validate your cases. And this also is a shift from that process where you sit down to be tweaking your grids and continually tweaking your grids until you get something that is well refined and good. In closing, I think he showed us also the strategic value that it brings, where it's going to help the marginal field operators to rapidly appraise their fields. How it also helps to do some update for the brownfield models, and in essence detect bypass oils, where possible, and also how it helps to reduce cost, because again, why spend so much on heavy computing where there are things that can help you run things faster than the way we presently work. So That is just, in essence, a very quick summary of the wonderful presentation we had listened to this afternoon. I will throw the floor open for questions. I'm sure some of us are really eager. But whilst I do that, please, I would like everyone to use their digital hand to give again a round of applause to Engineer Chukwuebuka for such a very, very wonderful presentation. Please, let's see your digital hands performing the applause for him. If we go to reaction, I'm sure we'll see it. I don't see hand clap from Warri chapter, please. Thank you so much, Adeseko. Thank you very much, Kai Mute. George, thank you. Thank you. I see all your hands up. Thank you so much. So I throw it open for question. I believe the moderator will also help me in terms of people who are raising their hands, as I would also be checking from my end. Please, is there any hand up? I see your hand up, Professor Juliet.
No. I was trying to do a clap.
Oh, okay. Okay, not a problem. Not a problem. So please, if you don't want to ask your questions directly, you can put them in the chat and I will read it. So whilst waiting for that, I've got question for you, Engineer Kizito, and probably after this call, we'll still discuss some more. One is, how do PIN, that's the PINNS, integrate physics into their training processes? I know time did not permit you to go deep into this, but I'd like to know how it does that. And then also, are there particular reservoirs that are suitable for this? Or do you just apply it to any reservoir? Because I know you did make comments about how you can help to be able to discover bypass oil. I know sometimes these bypass oils, we find them more in a very thin bed reservoirs. So please, let me use that to kickstart whilst the audience will provide some more questions.
Okay, thank you so much, Dr. Charles. And your summary was very, very, very splendid. Thank God this session was recorded, so I'll probably use that summary for someone else. Okay, your first question is, how do PIN teach or implement physics to machine learning models, right? Okay, so for every machine learning model, you add in constraints, right? And since for every machine learning engineer builds a model and adds certain constraints that he or she knows that model obeys, or that model has to obey. But then the mistake we make when we come for supervised learning or any unsupervised learning is we make it dependent on just the data or the historic data we have, right? But if we add a hard constraint, of physics, so we tell the model, okay, I want to build a model that has to do with fluid flow in porous media, for instance, right? There are certain laws of physics that controls fluid flow in porous media. We have that of Deci law, right? That controls permeability and the rest. We have that of conservation of masses. We have diffusivity law, and so on and so forth, right? If I train my model on these laws, so I tell it, you must obey these laws. These are hard constraints. When my neural network trains or interprets data, and peradventure the data is about to exceed or violate any of those laws, that's hard constraint. That's why it's referred to as hard constraints. Now, unlike soft constraints, whereby it would actually maybe disobey it, you get to see some If you check your MSE, that's mean square error, you get to see little errors here and there. These hard constraints must be obeyed. So what happens is it backpropagates. So I tell it you have to obey this. So since it has to obey this, it produces a result and validates that result against the partial differential equations, right? Now, I think the second slide or so, I talked about various ways of teaching physics to AI, right? That is what I just described now is one method. Another method is building it from the pipeline upwards. So there's a hard constraint method, which is the loss function method. Another method that is, what's it called? Becoming more acceptable is instead of PDEs purely, we are going into Fourier series. So instead of partial differential equations, we are using Fourier series to do this. So one of the methods is called Fourier neural operators, FNO. So if you are doing an FNO method, for instance, you are building this from the pipeline. So even if you train your model on, let's say, maybe a 64 by 64 grid system, that same model will be able to interpret a 256 by 256 grid system. That same model is able to expand and interpret a 1000 by 1000 grid system. I don't know if that answers your question.
No, very, very well. So I'm me not trying to be the chairman and also dominate the discussion.
Okay.
I'm trying to tend to say, okay, I mean, you've raised the Darcy's laws and the Fourier's equation that could be applied. Is there any particular one you use at any one time, or you must apply all three constraints? Because these are hard constraints that must be followed. Why I'm asking this again is because of the audience, and you have a mix of audience and experience level varies. So must you apply all, or you just have
yes,
you have to know which one to apply at any time?
Okay, you have to apply all because you are trying to, let's say I acquire a marginal field, for instance, right? Let's say I got a field from NUPRC at the last call, right? The information I get from that field is necessary that those information obey physical laws, or the result I get from a neural network I used to simulate that field is necessary that they obey each of the physical laws. Because if they obey one and disobey or violate the other, my result is wrong. So if you are obeying a diffusivity law and you disobey Darcy laws, for instance, that means everything about my permeability is wrong.
Correct.
Right?
You're very correct. You're very correct. Thanks. Let me not. We'll come back to the second question I asked, but let's hear Victor.
Okay,
please.
sorry,
Victor,
please remind me of the second question. Sorry, sir.
I'll remind you. Let's hear from Victor, and then we'll come back.
Okay.
Victor, your hand has been up since, so let's have your question, please.
Okay. Good afternoon, sir. Good afternoon, Dr. Charles. Good afternoon, Engineer Kizito. I'm so happy to be here, right? Because this is one area I have an interest in: machine learning application in subsurface geoscience. So basically, for me, I'm still a young professional, and so I'm big on learning, actually. So I kind of want to ask Engineer Kizito, for someone maybe that wants to learn, what do you advise? Okay, where does the person start, right? Because I know how to use traditional ML. I know how to understand the whole neural network of a thing, but I think this whole physics informed neural network, it's something I think I'm still new to. So what's your advice in terms of learning? How do I start? Okay, what do I need to learn? Thank you very much.
Okay, thank you so much, Sir Victor. My advice is very simple, and this advice extends even beyond learning physics-informed neural networks, right? I like to see myself as a learner, so I like to learn something new every time. And the way I do that is very simple. I always try to learn from the fundamentals. So that is why I still run a Reservoir Fundamental series every time. So what that forces me to do is I still go and read the fundamentals. So if you understand the fundamentals, you understand the Reservoir fundamentals, you understand machine learning fundamentals, you gradually build from there. So if you gradually, as you learn, you read other people's research. So you have learned the fundamentals, so you know what the fundamental laws are, you know what's you basically have the fundamental knowledge, right? Then by the time you read people's research, like I just got to know of FNO by weekend. How? After making my PowerPoint, I sent it to a friend of mine in the Permian Basin. Permian Basin is in the US. I sent it to him, and he also works. He had done something in physics informed neural networking as part of his PhD program. And I asked him to please evaluate if he could see any errors or loopholes or a knowledge that is lacks. He pointed out that, yeah, I knew I did not go into much of inductive bias as a method of teaching physics to AI. But specifically, I did not know of Fourier neural operators until just Saturday here. So you should be open to learning. One thing about AI is we could be discussing today and someone is already publishing something new on AI this very afternoon that is changing the past, or that will change the perspective of all we have learned today, or that will make us see this from a different perspective. So you have to keep studying, you have to keep reading other people's research and understanding the fundamentals. So if you understand the fundamentals, when you read other people's research, it helps you to build on what you already know. Thank you.
Yeah, thank you very much. Thank you very much, Engineer Kizito.
All right, thanks. Thank you, Victor. I also see Akajo for Faith. You had your hand up previously. Can you ask your questions? While we wait for Faith, I don't see any questions in the chat. I've not seen any other hand up, so please, let's ask the questions. Okay, Faith, are you there?
Right, Doc. So there are questions in the Q&A room, so I could just read them out. I don't know if that's okay.
Please go ahead. Yes, please.
Okay. Question from Akijo for Faith. She asked, what specific types of knowledge beyond basic PDEs are most promising for integration into these models, and how might this change the role of traditional reservoir engineers in the future? And for large-scale reservoir systems, how do PINs compare in terms of computational efficiency and scalability against conventional numerical solvers? I don't know if you got the question, Engineer Chukwuebuka.
Yes, I did. I'm looking at the questions too from this end. Okay, so our first question on types of knowledge beyond PDEs. So beyond PDE, I just spoke of Fourier series recently. So Fourier series is becoming more promising itself than PDE, right? Yes, I had to focus on PDE because my topic constrained me to PDE, but Fourier series is becoming more promising, right? Then how might this change the role of reservoir engineers? The only thing changing in your role, like Dr. Charles rightly noted, is you also have to have at least a basic knowledge of AI. And having the basic knowledge of AI, it is going to make your job faster. So it is not kicking you out of a job, certainly not. It's only making your job better, more efficient, and faster, and reducing the redundancy in your job, right? For large-scale reservoir systems, how do PIN compare in terms of computational efficiency, scalability against conventional numerical solvers? So against conventional numerical solvers, in terms of efficiency, it is better, because conventional numerical solvers depends to some certain degrees on your own iterative knowledge, your iterations and the rest, your guesswork and your tweaks, right, to a certain degree. Although, yes, I agree that you make those tweaks based on your knowledge of engineering or the rules of PDEs of physical laws. I agree. But then human error comes in, since I depend on you to make those tweaks. But if a neural network makes it based on those same rules, based on physics, based on engineering, and makes those tweaks for me, it is more efficient, right? It is faster. Now, computational efficiency also implies the weights. I have I noted I think towards the end of my slide, that we could pre-train, that is transfer learning. You could pre-train and then having a lighter weight model, a surrogate model, which runs faster on your system. So instead of spending 48 hours at minimum running a model, you could run your model in 10 minutes, right? So that means your system does not get drained or forced, and you too get enough time to do other jobs or other things. So in terms of scalability, you get to do more work for less time. So as Dr. Charles rightly noted, you get to do more for less, doing more for less. Thank you.
All right, thank you. I don't know if I'm to go ahead with the next question. Doc,
Yes,
should I go
please.
ahead? Okay. So, a question from Dr. Chukwuebuka, CG. She asked, thanks, Kizito, for the wonderful presentation. I understand that in the iterative algorithm using physics-informed models, the inverse simulation approach is compared with initial values to constrain the final results using an error margin. My question is, at what point do you optimize or stop the model iteration to enhance clarity of your model?
Okay. If I understand your question very well, at the point at which your pin stops that iteration is at a point whereby every data point obeys physical laws. So you already put in a hard constraint that this must obey our physics laws, our physical laws, right? So since you already have that in place, this model back propagates very fast. So if there's an error, it back propagates. If there's an error, it back propagates. As soon as it gets an answer that answers the problem and at the same time obeys physical laws on the other hand, so it answers the soft constraint and also respects the hard constraints, it's going to stop iterations. I don't know if that answers your question, Dr. Okugo.
All right, so I don't know if you would signify in the chat if that answers this question, it's our question. So I'll just move on to the next, which is from Joshua in tag, which is how do pins handle heterogeneous and anisotropic media, typical in reservoirs? Did you get the question?
Yes, I got the question. How do pins handle heterogeneous and anisotropic media typical in reservoirs? So heterogeneity is a big problem in our reservoir today. For me, I see it more as a blessing. So it simply means there's a high chance that I will report lesser oil today and tomorrow I get more oil. That is one perspective to look at it. So how do pin handle this? Pin handles this using collocation points. I spoke on collocation points earlier. So collocation points are points in the reservoir that are unobservable or that you don't have data for, right? So since we are handling a heterogeneous reservoir, I dare say that over 70% of the data in that reservoir, you don't have it. You barely got up to 30% of data from that reservoir, right? If we were to grade it in percentages. So, but PIN, respecting partial differential equations, or in this case, Fourier series, and applying the laws of physics, is able to predict, scatters points down all around the reservoir and predicts data for those points that respects the laws of physics. So yes, unlike other neural networks, supervised learning and the rest, that predicts points, yes, or predict reservoirs and make various predictions. These other predictions from PIN respect physics laws. So if you are trying to analyze your fluid flow in that porous media, your fluid flow in porous media respects Darcy law, for instance, right? It respects diffusivity law. So even if you are moving from coarse grid to an uncoarse region in your reservoir, to a fine region, sorry. If you're moving it from maybe a coarse to a semi-coarse region in your reservoir, it is able to predict and respect the laws of physics in those various individual regions and not just give you a single data point or a single porosity or a single permeability as the case may be. Thank you, Joshua.
Right. Thank you so much. Joshua, if you can just say if that answers your question. And Dr. Kirugo said thank you, you answered this question. So, yeah, and also Joshua. So moving on to the next question, which is from Owonipa Jason. He says, good afternoon, sir. I am a petroleum geologist with interest in machine learning for subsurface reservoir characterization. What method do you advise?
So the method I advise is, I think, is the same method I advised Victor. First, learn the basics. When I wanted to come into reservoir engineering, something very funny happened. And I like to tell people that is one of the things that dragged me to reservoir engineering. I visited my cousin. My cousin is also a reservoir engineer. And on his work desk, on his workspace, he still has fundamentals of physics. He still has engineering master's book. He still has, I think there's this secondary school master's book. He still has this popular chemistry textbook that we use those days. I'm trying to remember the name. Why did I forget his name? And he had Fundamentals of Physics by P.N. Okeke on his desk. So he gets to work, and once in a while, he goes back to read his Fundamentals of Physics by Professor P.N. Okeke and C.N. Okeke. He goes and reads his basic chemistry. He goes and reads his basic PDEs, mathematical equations, and the rest from his engineering master's. So I will tell you, start by understanding the basics. If you understand the basics, then you can build. So if the foundation of the house is not good, the structure will certainly collapse one day. So build your foundation, then gradually build on top of the structure. Thank you.
All right, thank you so much, Engineer Chukwuebuka. I think that's our last question. So I'll kindly have to hand the mic over to Dr. Charles. Sir?
No, thank you for helping to sort out the Q&A session because I couldn't see them. Again, Dr. Kizito, thanks for this very insightful and educative presentation you gave. I'm sure you saw the buzz on this, and I'm pretty sure many people would want to ask, probably have so many questions to ask. You and I can call you up later, and then we'll have some other discussions around bouncing off ideas on things like this. So thank you so much.
I would appreciate that, sir.
I'll pass it back to Professor Juliet, the chairperson for Warri chapter, to take over the meeting from now on.
Okay, so thank you so much, Dr. Shaz.
Yes.
Dr. Shaz, thank you so much. We appreciate you.
Thank you.
Thanks everyone that have find time to ask questions. Our speaker, Dr. Kizito, thank you so much. So I believe our PE is on the call now. PE, are you there?
Yes, can you hear me?
Oh, okay. So you can help us appreciate our speaker and the chairperson for today.
Yeah, thank you very much, Warri Chapter Coordinator. Yeah, it's been an insightful one. First, I would want to say thank you to the chairman, Dr. Charles Otoile, for finding time to anchor this session for the Warri Chapter. Dr. Charles, well, that's my friend, known very well. So I'm not surprised that he did a yeoman's job. He did it well. Thanks, Charles, for anchoring this for us. And then to also appreciate the presenter, Engineer Chukwuebuka Kizito. At this point, I would like to hand over the award of appreciation to him. So this word of appreciation is given to Engineer Chukwuebuka Kizito Duru for the presentation, match presentation on production production programmer, sorry, and then West One Asset for Renaissance Africa Energy. So thank you very much, Engineer Chukwuebuka, for your time and finding time to present this topic to us. Also, this award of appreciation goes to the chairman of the occasion, which is Dr. Charles Otoile, FNAPE. He's a senior account manager with SLB. SLB is Lombiji, for those who knew it with the old name, or who knows it with the old name. He's the chairman of the technical business meeting for March 2026 for Warri chapter. Thank you very much, Dr. Charles Otoile. So at this point, I'll hand over to the Warri chapter coordinator. Thank you.
Thank you so much,
Okay,
Dr.
thank you,
Anthony.
P. Thank you, P. So before we go to the announcement, let's just do a group photograph before we go to the announcement. Let's on our video. Uta, get ready. Uta, are you there? Get ready. So today, please, just let's on our video so we can do the group photograph. We're going to go to the announcement. Today, are you there? Hello, today, are you there? Because let's just do it now. A lot of people are dropping off the call and before. Today, are you there? Okay, Kalisto, can you help us with this now? Let me try and beat it up. Just a minute. Okay, today help us do this now. Please, let's on our videos, please. Today, are you there? Are you done?
Okay, I'm there. Sharing the screen.
Okay, once you are done, let us know. Are you done with the pictures? Hello, today you're supposed to be snapping us.
I didn't have all from the group. So
Okay,
Hello,
is the
today.
PS going to speak through it? Can you see the screen now?
It's not the screen. We need to snap us. Do the group photograph.
Okay.
And that's all we're asking.
All
Maybe
right.
you didn't get it. No.
I can see the screen. I can see the screen, but hello, can you hear me?
No, just hold on. Today has not confirmed it's true. It's like he didn't. Today, I confirm if you are true with the group photograph.
No, just hold on. I'm sorting it out now. So let's stop screen sharing first.
Okay. Okay then.
Okay, it's done. Thank you.
Okay, okay. So let me go back to share the screen. Okay, so Sunday, I just Sunday, are you there? Is that Sunday? Are you there? You can go ahead with the announcement.
Yes, I'm here.
Okay, so go.
Confirm if you can hear.
We can hear you. Go ahead.
Okay.
Yes, you can go ahead. We can hear you. You can go ahead.
Confirm if you can hear me. I don't know if you can hear me. If anybody. We'll be having
We are confirming
our
to you. We can hear you.
epoch-driven tectonic modeling for complex fault networks, overcoming seismic imaging challenges. And this will be anchored by two speakers in the person of Bogodov Daniel, head of AI R&D, Geoplat AI, Moscow, Russia, and will be co-handled by Ayo Mustafa, MBA, PM, in Kase, CEO, Bizday Technology Consulting Limited, New Jersey, USA. So let's keep a date with us. That will be taking place on the 7th of April. Let's keep a date. All right, so the NAPE Annual International Conference and Exhibition will be coming up November from 9th to 13th. Let's keep a date with that. Early bird registration is ongoing and it will be taking place in Eco Hotel and Suites, Lagos. So early bird registration will be on and it's still ongoing. It will be on till September 1st. For members that are financially up to date, you have to pay an amount of 100,000. Non-members, 110,000. Lecturers that are financially up to date will pay 60,000. Students that are financially up to date will pay 40,000.
Okay.
And internationals are required to pay $275. All right. Now, after our early birds,
okay, sorry about that.
Members who are financially up to date are required to pay 110,000. Non-members 120,000. Lecturers 70,000. Students will be 50,000. Internationals will be 285,000. So let us make use of the early bird window.
I will do. I will.
The monthly technical meeting sponsorship opportunity is still very open. The 2026 technical business monthly meeting sponsorship is still very open for interested partners. For more details, you can check details on your screen. The non-pay membership dues is what really qualifies you as a member, as a financial member. So for student membership, the dues is 2,000 naira. For active membership, is 12,000 naira. For associate members, 12,000. Corporate members, 50,000. Please pay your dues to avail yourself some of this opportunity and even more. Bank details is shown on your screen. If you can see UBA Bank, you can pay into the NAPE account. The fundraising drive for the purchase of permanent NAPE secretariat is still ongoing. Please, let's try to contribute into this course. For fellows, it's required a minimum contribution of 250,000 naira. Active members, a minimum of 150,000 contribution in naira. For lecturers, we're required to contribute 75,000 naira. The account details is also showing on your screen. Let's please key into this fund raising. Thank you very much. That will be all.
Can you hear me? Okay, I was muted. I was speaking. So thank you so much, PS. Over to Dr. Wilson Oson. Dr. Wilson, are you there? Hello, Dr. Wilson. Dr. Wilson, are you there? Okay, let me call Dr. Kenny. Can you hear me? Dr. Kenny, can you hear me?
Yes, I can hear you.
Please, Dr. Wilson, maybe network dropped him. I just go ahead with the put of that.
Oh. Sorry. On behalf of the NAPE Warri chapter, we want to thank everybody that has attended this meeting.
Hello, my connector.
Okay.
Okay, you can hear me now. Okay.
Yes, I had an issue with my network. I will repeat right now.
Okay, you can go ahead.
Okay. Well, I want to really appreciate all the person on the call. And we had our president and our VP, Emmanuel on the call. We actually had some fellows on the call. I want to say a very big thank you. This topic is actually very, very essential to ensure that we all have better learning abilities. I know that Warri is always setting the pace for others to follow. Thank you for coming around. And I believe by next month, God willing, we'll have a better topic and we'll need to improve on what we have done for this particular month of March. Thank you very much.
Thank you, Dr. Wilson. Thank you so much. Thank you, everyone. And Kenny, thank you for trying to stand in for Dr. Thank you so much. We appreciate you always being there. Thank you. RP, thank you so much. President-elect, we appreciate you. Thank you, everyone. Thank you to the speakers, Dr. Charles, everyone that is on the call. We say thank you. Warri chapter appreciates you. And NAPE at large appreciates you.